Hello, everyone. This is Geoff Mendenhall. I'm the retired Vice President of Engineering for the former Harris Corporation Broadcast Communications Division, which is now known as Gates Air. And I'm speaking to you from my ham shack, which is located on Catawba Island. I'm on the west end of Lake Erie off the north coast of Ohio. It is an honor for me to make this presentation to the Radio Club of America today. Especially during the month of November 2020, which is the 100th anniversary of the start of AM broadcasting in the US by KDKA in Pittsburgh. One of the latest modulation techniques I'll be talking about, 3DX, is currently being used at KDKA, and I'll have a photograph of the transmitter a little later. I might add, I grew up listening to KDKA from my hometown of Johnstown, Pennsylvania, which is about 60 miles east of Pittsburgh. Okay, let's see if I can get switched over here to share my screen. And I guess it's up okay. Does it look okay, Jim?
Not showing yet, Jeff. Maybe having some of those gremlins coming in like this morning.
Okay, let's see here.
It worked perfect this morning.
Yeah, let me tab back. Okay, share.
There we go.
Yeah, here it's coming. Okay,
and,
you're good to go.
We'll put her up full screen. How's that? Full screen?
Looks great.
Yes.
Okie dokie. All right, we're very good. Okay, well, let's see here. I'm going to be talking about various modulation techniques. There have been many methods developed over the years to AM modulate a transmitter, going all the way back to carbon microphones. Somebody mentioned that earlier. They actually use high power carbon microphone in series with the RF lead to the antenna way back when. Later on, some other methods have evolved, some having higher efficiency and fidelity than others. This presentation is going to be a brief overview of 5 of the more recently developed AM modulation technologies. And 4 of these technologies were invented by Hilmer Swanson, the 5th by Kai Liu at the Harris Corporation Broadcast Division, which I now mentioned is now called Gates Air. And I had the privilege of leading the design team that developed several of these technologies. So the progression of high-level AM modulation. Back in the 50s, things kind of got standardized on Class B high power modulation, where you had a high power audio amplifier capable of about 1/2 of the RMS power of the RF power amplifier. A little later, Western Electric and Continental both developed transmitters using the Doherty technique, which uses 2 power amplifiers, a carrier PA and a peak PA, and they're connected by an impedance inversion network. And then about that same era, McClatchy Broadcast, in cooperation with the RCA, Radio Corporation of America, developed a technique called Ampliphase, which used 2 RF power amplifiers which were outphased. ABB and Switzerland, Continental in the US, and Harris also used another technique called pulse step modulation, a pulse step power supply. And that was primarily used for high power shortwave, HF shortwave transmitters. So the last 5 I'm going to talk about here were developed at Harris, a pulse duration modulation, progressive series modulation, and then an advancement to PDM, which is polyphase pulse duration modulation, DX, which is a method for direct digital synthesis of the RF envelope, and later 3DX Gen 2 direct digital synthesis. All this was brought about by a quest for efficiency and fidelity in AM broadcasting. Classical Class B modulation, of course, required magnetics in the form of a transformer and modulation reactor, and suffered somewhat from limited frequency response and distortion limitations. Prior to that, transmitter efficiencies were only between 25 to 50%, so there was a great need to improve efficiency as well as fidelity. And later, there was a need to extend frequency response from DC to beyond 40 kilohertz. And I'll say a little more about why would you need to go beyond 40 kilohertz or down to DC, but there's a reason for that. And then the reduction in distortion, certainly to less than 1% total harmonic distortion, and eventually support for envelope deletion and restoration, which will allow an AM transmitter to transmit any arbitrary waveform, including digital waveforms. So the first one I'm going to speak about is pulse duration modulation. It was developed in 1970 by Hilmer Swanson at Harris Broadcast. It was an extension of pulse width modulation to meet the bandwidth and distortion requirements for AM broadcasting. And it was first applied to vacuum tube RF amplifiers and then later to solid state amplifiers. This improved the overall transmitter efficiency up to about 65%. PDM is a switching technique that is used to create an analog modulated voltage, which is then applied to the RF power amplifier. The RF amplifier stage is high-level modulated by a filtered analog output voltage from the PDM switching modulator. The modulator switching frequency must be removed, though, by an analog filter between the modulator and the PA. And the switching frequency is limited by system linearity. In other words, we can't just go to some arbitrarily high switching frequency. There's limitations on how far that can go, especially at high power levels. Here's a simplified schematic of a solid state PDM transmitter, but the same idea applies to all PDM transmitters. Over here in the lower left, and Jim, are you seeing my cursor okay? I want to check on that.
Yes, it's coming through fine, no problem.
Okay, so this is the PDM generator. Really, it just consists of a voltage comparator that is sampling a linear ramp waveform at the sampling frequency or switching frequency and the audio waveform that's being modulated. And this comparator then converts that into a series of rectangular pulses, and their pulse width or duty cycle is dependent upon where the switching occurs on the analog waveform. This is then fed to a switching device. In this case, we're looking at a solid state FET device, but it could be a vacuum tube as well. This device is connected in series with the DC power supply that feeds the power amplifier. So the DC supply is switched here, and then it is fed through a low pass filter, which filters out the PDM switching frequency and integrates these pulses back into a smooth analog waveform that then is applied to the power amplifier. So here's an idea of what this would look like. Here you see the sampled analog waveform, and you see the pulse widths varying depending upon the instantaneous amplitude of this waveform. At the output of the integrating low-pass filter, we get an exact replica of this analog waveform, just much bigger. It's been amplified, and it's at a level that can actually power the high-power RF amplifier. Here's another simplified schematic showing an implementation of PDM with a tube. In this case, we have the RF tube at the top of the stack here. In this case, this is a 50 kilowatt transmitter. It's about 18,000 volts applied to the plate of the tube. And then the negative return from the RF amplifier is fed through the integrating filter and through another tube, that's being switched hard on and off into saturation and off, driven by the PDM waveform. Looking at a little more detail here, this is a diagram of a 50 kilowatt PDM transmitter. Specifically, this is a Harris MW50, which was in use at KDK at one time as well. In this particular transmitter, the entire RF system of the transmitter is in this rectangular block here. It's all isolated and floating at 18,000 volts, or actually it's higher than that. It's about 25 kV for the MW50. And then the isolated box, as we called it, the RF amplifier system, is returned to ground through the low-pass integrating filter and through a switch tube at the bottom of the stack, which is pulse width modulated again by the PDM circuits. This is a photo of what a MW50, a 50 kilowatt tube type PDM AM transmitter looked like, 4 racks wide. Now we'll move on to progressive series modulation. This is an interesting technique that is useful for lower power transmitters. It was developed in 1974 for the Harris MW1A, which was the first all solid state AM broadcast transmitter. This technique is a quasi-linear series modulation technique. It divides the power amplifier DC power supply in half. So there's half the power supply is at carrier level and half at peak modulation level. This was done to improve efficiency, the frequency response. So this was literally from DC to 15 kilohertz. There were no magnetics involved, so no limitation there. And the total harmonic distortion was less than 1.5%. The overall efficiency was fairly good, about 50%. Here's a simplified concept of PDM. So here you have the RF power amplifier, and an unmodulated condition at carrier, you have a 70 volt power supply here that's routed through this diode and down through a transistor that is turned on, saturated, so there's very little dissipation in it. So we have the 70 volts applied to the power amplifier. And that generates our 1 kilowatt carrier level. When we positive modulate this transmitter, this upper transistor starts to turn on, and it's connected to a 140 volt supply, twice the 70 volts. To 100% modulate the AM transmitter, you've got to double the voltage on the power amplifier. So this transistor then starts to turn on and follows the waveform. Meanwhile, the bottom transistor remains saturated. And during the other half of the modulation cycle, when we go below carrier power, the upper transistor turns off and the lower transistor comes out of saturation and starts to provide a variable voltage drop down to the power amplifier, basically all the way to 0 voltage at 100% negative modulation. So this was done to limit modulator dissipation, splitting the power supply. There's no dissipation at carrier. Dissipation is lower in the lower device is only when the RF envelope is below carrier, and dissipation in the upper device is only when the RF envelope is above carrier. The modulated efficiency is about 50%, which is okay for a kilowatt, but it's not, obviously not as efficient as PDM and not as useful for high power. And this is a photo of the Harris MW1A transmitter, which was PSM modulated. Now we'll move on to the next generation of PDM, or pulse duration modulation, called Polyphase PDM. A single PA, Polyphase PDM system, was patented in 1979, followed up by a multiple PA Polyphase PDM system that was patented in 1984. Polyphase PDM was the next advancement in AM technology. Main advantage is it offered a higher effective switching frequency, and that would allow us to extend the modulation frequency response by moving the integrating filter cutoff frequency higher. And that thereby overcame some of the filtering limitations of single phase PDM, which would be better frequency response and better phase response of the modulated waveform. Here's an idea of how PDM waveforms work. In this case, we have 4 phases. So these phases are offset in this case by 90 degrees. So some of you may be familiar with just a 3-phase polyphase rectifier in the AC power distribution world. The idea here is the same by having multiple phases that are offset with each other. The effective ripple frequency of the system is increased proportionately, and so therefore the filtration of these pulse width modulated waveforms is eased. The cutoff frequency of the integrating filter then can be moved out to a higher frequency. Here's a block diagram, simplified block of what I would call a single PA. We have a single RF amplifier here but we have multiple modulators. It could be 4, it could be 8, it could be up to 18, it could be any number you wanted. Typically, number of PDM modulators used for practical purposes is about 4. So each of these modulators is running slightly offset in phase, and then the integrating filter network is designed so that the output section of it can sum all of the currents from the various individual filters into a single output, which is a single integrated waveform that has the switching frequencies removed from it. There was also, as I mentioned, another design that used multiple subsystems, each one having its own PDM modulator and RF amplifier. So this is basically a complete transmitter system, each one of these 4 blocks. And so the actual summing of the outputs was done in an RF combiner rather than at the audio or integrated audio prior to a single amplifier. So this is the multiple amplifier PDM system. This was really never converted into a commercial product. It seemed like the single PA with multiple offset PDM modulators turned out to be the most practical approach. And here's what a solid state 5 kilowatt Harris PDM transmitter looked like back in the 1980s. So that's a single rack, solid state 5 kW, and it's a polyphase PDM modulated. Now we get on to the really interesting stuff from my point of view. This is what was branded as DX. It is a form of direct digital modulation. In this case, we directly synthesize the RF envelope by using a series of digitally weighted RF voltage sources. Think of this transmitter as output stage as being a 12-bit high-power RF digital to analog converter, which is fed by digitally converted phase and magnitude components. So another way of stating that is you take the audio, you digitize it, and then you drive this digital to analog converter, which directly synthesizes the RF waveform. This technique completely eliminated the modulator stage and the analog filter requirements, which now allows modulation bandwidths of greater than 40 kilohertz. And it also allows the generation of any arbitrary RF waveform very accurately and is very relatively unaffected by VSWR or PA module failures, load changes on the RF output stage. This is done at a sampling rate that's either at the carrier frequency or a multiple of the carrier frequency. An RF bandpass filter on the output of the RF power amplifier is used to remove the image spectrum, which includes an image at twice the sampling frequency and a DC component. Automatic reassignment of failed modules is possible. And the highest AC to RF efficiency has been achieved this way. It's about 88% from the AC power input to the transmitter to the RF output to the antenna. Direct digital waveform synthesis also provides a very high accuracy envelope elimination and restoration. This is used to create an OFDM or any other arbitrary RF waveform, including single sideband or any other waveform that involves both amplitude and phase components. What's really important for EER is very close tracking between the envelope and the RF phase channels to the RF output stage to accurately recreate these waveforms. Here's a simplified concept of DX transmitter. We have a series of equal step RF power amplifier modules. Depending on the size of the transmitter and the vintage, it could be anywhere from about a kilowatt a step up to 3 kilowatts per step. And then we have a series of smaller, what we call binary steps, half voltage, 1/4 voltage, 1/8 voltage, and 1/16 voltage. So the audio input to the transmitter is encoded. It's done through a 12-bit A to D converter, and then the encoded audio is used to turn on and turn off the correct number of large steps and small steps at any instant in time. The magnitude is sampled every carrier cycle, converted to 12-bit word, and the 8 most significant bits turn on and off the equal RF voltage steps, and the last 4 significant bits control the binary steps to fully synthesize the waveform. You can see this a little better here in this picture where you see the equal steps, and then to fill in, to get the resolution to fill in between the larger steps, we have the binaries. Again, half, quarter, 1/8, and 1/16 of each of the larger steps. Now, envelope elimination and restoration is a technique that allows a nonlinear high-efficiency amplifier, not a linear amplifier, high-efficiency nonlinear, to amplify any arbitrary waveform, including OFDM, which is an orthogonal frequency division multiplex, multi-carrier that's used in HD radio and other digital systems. HD radio, DRM is another one, or even single sideband. The RF waveform is decomposed into separate amplitude and phase components. Instead of I and Q, you can also use A and theta. The transmitter is simultaneously modulated with separate amplitude and phase modulation components. Now, to do this correctly, you have to have high modulation bandwidth, approximately 3 times the waveform bandwidth. And as I mentioned earlier, very close tracking between the magnitude and phase channels to the output stage of the transmitter. The DX technique eliminates differential envelope versus RF phase between the modulator and the PA, which you would have to compensate for pretty severely if you had a PWM or PDM filter involved. So DX eliminates that need. Just a little review of here's any arbitrary digital constellation point can be represented either by I and Q, X and Y, or by a vector length amplitude A and a phase angle theta. I'll take just a second to talk about superpower DX transmitter blocks. This is a 600 kilowatt solid state AM transmitter having 3 200 kilowatt power blocks. And then these are recombined into higher power levels. We built systems up to 2 megawatts of carrier power and with 100% modulation or even above 100% modulation, 8 to 10 megawatts of peak envelope power. So you can see where these power blocks, 200 kilowatt power blocks are combined, and then that combiner is recombined with another group to go as high as we want to go in power level. Here's a picture of Hilmer Swanson testing a 2 megawatt DX transmitter. So this is 1 megawatt worth of power blocks on this side and another megawatt worth here. And we have had installed quite a few of those. Back in 2009, we had 2 of the 2 megawatt systems and 2 megawatts, 5 of them 1 megawatts, and so on. So a lot of this high power, none of it in the US, of course, 50 kilowatts is the maximum. They could have used one at WLW back in 1925 when they were at 500 kilowatts, but that didn't happen. Okay, so DX evolved into 3DX. What is 3DX? Well, it was invented by one of Hilmer's proteges, Kai Lu, at Harris in 2000. It's what's currently in use at KDKA. They have a pair of 3DX 50 kilowatt transmitters. The main difference between DX and 3DX is we moved from to direct digital RF drive to the PA modules. The original DX still had RF intermediate power amplifiers and RF distribution splitters to the modules. 3DX, the RF originates right in each module, and it's just direct digital drive through a Cat5 cable. We also converted to a distributed modulation encoding and structure. There, every 16 modules has its own mod encoding structure, so it can be fanned out indefinitely. And the most important thing about 3DX was the change from a thermometer type sequencing of PA modules. If you go back and think about that drawing I showed of the modules being turned on and off, at carrier, about half the modules are on all the time. And then as you go above carrier, the peak modules come into play. As you go below carrier, all the way down to 0 RF output, all the modules are turned off. But obviously, the modules at the top of the stack are used less than the modules at the bottom. The ones at the bottom are on almost all the time. Well, we went to a system of circular rotation of module assignments. So we completely reassign the modules in the stack continuously to spread the heat evenly. So all of the modules operate, their duty cycle is all the same regardless of where they are in the modulation sequence. And here's a photo of the two 50 kilowatt 3DX transmitters that are currently in use at KDKA. Each one of them is 3 racks. So just to summarize, we've covered 5 recent modulation technologies. All of them improved efficiency, reduced distortion, and improved the modulation bandwidth. You know, PDM was kind of the first in the group. PSM came in there as something for low to medium power, then Polyphase PDM, DX, and now finally 3DX. And with that, I will open it up for questions and answers. And my contact information here is on the slide. If anybody wants to email me, I'll be glad to have a dialogue with you. So go ahead with the questions.
Geoff, thanks very much. Great presentation and tremendous even history and everything. It's just phenomenal what you did in 30 minutes here this afternoon. So let's go to Q&A. And if you have a question, please put it in the chat or in the Q&A area. And so let's go to Trey for our first question for Geoff Mendenhall.
I'd like to start with a question of my own, which is you're talking about these 1 and 2 megawatt transmitters. Who are the customers?
Okay, most of those customers are foreign governments, as well as the Voice of America. We have several 1 megawatt transmitters at Voice of America, Kavala, Greece, one north of Bangkok at Ayutthaya in Thailand, a couple at Point Poro in the Philippines. We have a 2 megawatt one on the north tip of the Gadar Peninsula. That belongs to the government there. That is a real flamethrower, by the way. Ben Dawson and Ron Rackley, some of the others worked on the antenna system for that. That was a 2 megawatt transmitter. It's located just a few thousand feet from the saltwater on the north end of the peninsula there, and it goes into a 4-tower directional array with about 8 dB a gain. So when you add it all up, the peak PEP radiated power in the direction of the main lobe is close to 50 megawatts. So that station put in a city grade 6 millivolt signal into Kuwait City, which is about 600 miles north. That was, we won't say ground wave, that was sea wave over saltwater.
Boy.
So those are the primary customers. We also did a couple of long wave stations for governmental agencies as well. So.
Very cool. Barney, how about a question for Geoff?
Okay, I see several have popped up here. One of the maybe simple ones, and what efficiency do you get from 3DX?
Well, the overall efficiency of the system is about 88% for the total transmitter. That's from the AC input to the RF output. The efficiency of the modules, the PA amplifier modules, is up in the mid 90% range. But then you have the overhead of the cooling fans, A lot of these, the very high power ones are liquid cooled. So you have some overhead with the pumps, liquid cooling, the control circuits, the loss in the magnetics for the primary power supply and so forth. So that gets you from 95% down to 88%.
Very cool. Trey, a question for Geoff.
Do these AM modulation advancements enhance any other transmission spectrum ranges, such as FM, C-band, KU band, etc.?
Well, envelope elimination or restoration can be used. It's used in FM for HD radio. You know, with a current standard broadcast transmitters, Class C saturated nonlinear amplifier, when they add HD radio to it, you need to have some amplitude modulation. And so that is added in by simultaneous amplitude and phase modulation on of the transmitter to add that on top of the FM.
Barney, another question for Geoff.
One of the early questions was Joe Huey K2PLY or PEY involved in any of these designs?
Yes, well, Joe is my boss. he's the best guy I ever worked for. I don't know if he's listening, but it was great working for Joe. And yes, Joe was a big proponent of DX, and he was a general manager at Harris Broadcast during part of this era. So he is well aware of it.
Hey, Geoff, any broadcast transmitters living at your QTH currently?
Well, there's a Harris MS-15 FM exciter in my rack. It's being stored there in the background. Nothing AM. There is an FM exciter here. It's not hooked up to anything right now. It's just being stored in the rack, but it's one of the few trophies I have from my career.
I've got a Gates BC1T here.
Oh yeah, well that would be good. You know, I wish I had some old heavy iron. I'll put a little plug in for the Greater Cincinnati Amateur Radio Association. We're having our annual AM night. Normally we're a sideband net, but at 9 p.m. Eastern time on Thursday night before Christmas this year. It's early. I think that's December 17th. We're going to actually start early, but we're going to have our annual AM night. There will be a lot of heavy metal on the air. So any of you guys that got broadcast rigs that can get on 1936 kilohertz, show up. I don't have any heavy metal. I'm going to be using a flex radio driving a homebrew linear amplifier. So, but I'll put a plug in for that.
Very good. And Trey, another question for Geoff.
Geoff, at the beginning of your presentation, you mentioned that you'd get back to us and explain why DC to 40 kilohertz or greater bandwidth was interesting or appropriate. Can you elaborate more on that?
Yes, well, the 40 kilohertz goes back to if you want to use envelope elimination or restoration to add a digital waveform, you got to have about 3 times the modulation bandwidth required. So for DRM or HD radio, you need about 40 kilohertz of modulation bandwidth capability in order to get to eliminate, well, get good linearity of the system and to eliminate spectral regrowth on either side. And on the DC side, the way that we control the power output on a DX transmitter, and this could actually be done on some of the PDM transmitters, is you just control the DC offset to the PDM modulator or the A to D converter and adjust the carrier level that way. So you simply can control the output of the transmitter by just adding subtracting a DC component to the audio.
Barney, another question for Geoff.
Oh, let me add one more thing to that. Beyond that, there's a thing called modulation dependent carrier control, MDCL, which is used to improve the efficiency, particularly on shortwave transmitters. But some broadcasters in the US are using MDCL as well. And MDCL also uses the DC component in the audio to control the carrier level, to actually reduce the carrier level during certain portions of the modulation cycle.
Okay, Barney, another question.
There a question popped up as what is greater than 100% modulation?
Okay, it is possible to modulate an AM transmitter to greater than twice the carrier level, and to do so without introducing much distortion to an envelope detector. Typically in the US, most broadcasters with modern equipment and good audio processing typically modulate to plus 125% on the positive side, but of course they can't go beyond negative 100%. They cut off the carrier clip. So they use audio processing to asymmetrically modulate the transmitter. The Harris DX transmitters are capable of about 150% modulation if all the modules are online. That's another thing. If some of the modules were to fail, the transmitter keeps working, but eventually you start to lose a positive modulation peak if you don't have enough modules left to create those peaks. But most US broadcasters that are heavily processed are running over 100% positive peaks.
Trey, another question for Geoff.
Jonathan Rizzo asks, which format do you believe is better for digital AM, HD radio MA3 or DRM?
I think they're somewhat equivalent. I think that MA3 is actually a little bit better in terms of the bandwidth utilization, but they are very similar. DRM has a little bit higher peak to average ratio that has to be accommodated by the transmitter because it's a pure OFDM signal. So now in the hybrid mode, if you're just talking pure digital, I think they're roughly equivalent.
So Geoff, can a DX transmitter today be upgraded to DRM or changed to DRM?
Yes, yeah, and in fact they're running DRM several places. They're testing it. As I said, the DX transmitters can transmit any arbitrary digital waveform. So it could be DRM, it could be HD radio MA3, it could be 64 QAM, you name it. In fact, we used DX transmitters with a project the U.S. Coast Guard had for digital nav techs, and that used 64 QAM OFDM.
Okay, and Barney, another question for Geoff.
There was a question here commenting about he was impressed with the antenna testing range at Harris. Can you tell us a little bit about their testing facilities, antenna testing facilities?
Well, at one time, Harris Broadcast in Quincy, where I lived for 26 years, had, I think, the world's premier antenna test site at Palmyra, Missouri. It was located on a river bluff. It was kind of a sheer drop off over the Mississippi River Valley. And it was a great range with all the far field turntables and everything you could imagine. Unfortunately, it was decommissioned when Harris sold that business to Dielectric Communications. That range went defunct. Dielectric does have a far field range as well, but more importantly, and I think we're going to hear this from one of our other speakers later today, is that a lot of the far field measurements have been negated now by near field measurements using method of moments, computerized methods and probing methods, so they can derive the same kind of pattern information without having to actually put an antenna on a turntable and get hundreds of feet away from it to measure it.
Trey, another question for Geoff.
I just had one more question from myself as a guy who doesn't know too much about broadcasting. You showed us a photograph of a pair of 3DX 50 kW transmitters at KDKA. My question is that like a primary and a failover backup? And is there some sort of failover systems in broadcast stations? Can you elaborate on that a little bit? Yeah,
those are main alternate transmitters. I don't know exactly how Chris is running them now, whether he's running one week and the other week, or whether one is just in reserve. It's different operators have different methods of using them, but both the transmitters should be maintained fully operational with an automatic failover capability. Chris, are you online? Yeah, I see you there.
I'm still here. We use the main alternate main approach, and I rotate them out. But you can consider it a main and a hot standby backup, if you will. The newer transmitter, obviously there were several versions of the 3DX. I have one from, say, 2000 vintage and then one from 2007. So now, to keep the hours equalized on them, I have my lean-to on transmitter 2, which is the newer of the two. And but either transmitter is fully functional and capable of supplying power to the antenna.
Boy, they sound
Thanks,
good,
Chris.
Chris. They sound just tremendous.
Digital transmission.
Yeah, it's just beautiful. I want to remind everybody to make sure you fill out the evaluations for our speakers today, and the link to that is Amy's been putting that in the chat room, so make sure you do that. And we still have a few more minutes here with Geoff, and thanks very much for coming on, Chris. Barney, another question.
Yes, Geoff. Someone asked if you could give us a brief tour of the equipment behind you.
Okay, I'll try and do that. Hang on. I'll pick up my computer and walk over here. Let's see. Oh, wait a minute. I gotta go full screen to myself so I can see what I'm doing here. Hang on a second. Speaker view. Let's see. Well, let's see. Yeah, I'll just use the little window here. Okay, so I'm in my retirement digs here. So this is my ham shack. There's all my DXCC awards up there on the wall. Okay, so when I built this house, I'll get out of the picture here. I built 3 equipment racks in, and they're built into a wall. And so I have all my ham gear in my operating position here. So my main radio is a Flex 6600. It's sitting there running on 20 meters right now. That's FT8 waterfall that you see on this screen above it. I have a backup ICOM 756 Pro. I get Tokyo high power amplifier there. A Halstar AT Auto and a manual Tentec tuner there. There's my my Harris MS-15 resting in the rack there. It's just being stored there. I don't have an FM antenna hooked to it. Then I got my audio chain here. So I actually have my audio chain is I have a Heil PR40 microphone, and it goes into a pair of Symmetrics 528Es, which are the mic preamps and equalizers. And there's a Dixon mixer that selects my microphones. Up above that is an Orban. Let me turn on the light here. There, you can see a little better. There's the Orban Optimod, right? Broadcast guy, you got to have a broadcast audio processor. So that's an Orban 9200. So that's my audio chain. And then that 9200 drives the line inputs to the Flex 6600 and the ICOM 756. And then here's Big Bertha down here. She's my original homemade linear amplifier, a pair of 3500Zs. And that has origins back to high school days and it's been improved upon over the years. So that's kind of a tour of the rack. Now, interestingly enough, take another second here. I'll click on the lights here. So I got I have these racks in a wall. The other side of the wall here is my laboratory, and that's all my test equipment mounted on the back side. And then this is in between the racks. Looking in, you can see the ham radio gear on one side, and you can see the back of the test equipment on the other side. So that's my little room within the room for all that gear. So anyway, that's enough for ham radio, but hopefully the hams enjoyed that.
So Geoff, when they told you had to shelter in place, what a place to shelter in, huh?
Yeah. Well, yeah, besides the ham shack, I've got a beautiful place to live here. I walk every morning along Lake Erie lakefront, do a 3-mile walk, and you know, I can't think of a better place to be trapped.
Well, again, Geoff, thanks so much for coming on today and giving us this wonderful presentation.